I'm just going into my topic, feedbacks, thresholds, tipping points in the climate system. It's a big topic, as you have seen already. And I'll try to go a little bit deeper into it, because I have heard that you're a very diverse audience coming from different perspectives. And so I thought I'm explaining it a bit better than normally. Now, that the Earth is warming rapidly, I think we all know. Specifically, during the last 30 years, we have an unprecedented warming, at least since we record temperatures globally. And this is also seen in the global land temperature anomalies that really start in the 1980s to be quite significant. And if you just look into the last 6 years, they have been the hottest years since the recording, right? Since on record. And that's something that is known to everyone, but it's also disturbing a bit. And today we should, in a way, try to discuss what consequences that can have. So what this high temperature also means for possible feedback reactions. Now, the reason why we have this warming is because we have a radiative forcing that you see here by different forcing agents. And the most prominent one is certainly CO2, carbon dioxide. But we also have or other greenhouse gases, non-CO2 greenhouse gases like methane or nitrous oxide or halocarbons that contribute quite significantly to this radioactive forcing, which at the present is above 2 watts per square meter globally. Sure, we also have tropospheric ozone, for example, and we also have some interactions of aerosols with clouds, for example, that are actually cooling the Earth. But overall, anthropogenically, we have about 2.2 watts per square meter radioactive forcing. And this is now calculated for the last 160 years. Now that's significant, and that warms the Earth. And if you just look into the CO2 again, then we can see that the CO2 is rising without, like any sign of a slower rise. We have heard a lot on lower emissions during the last years. Yes, there were lower emissions of about 5 to 6% globally, but this is not really halting the atmospheric CO2 increase. Here measured, for example, at the Mauna Loa, and you see it's ever increasing. In fact, it's even accelerated a bit. And the latest data that we have from April this year, just last month, is that we are on average on 419.05 ppm CO2 in the atmosphere, which is really a lot. When I started the first measurements as a student in my student course, they have been below 350, right? So we are always saying, it's increasing, it's almost 350, and now we are at 420. So that's a significant increase, and certainly that has consequences. Now, if we want to predict what happens in the future, we need to actually think about climate sensitivities. And this climate sensitivity usually is calculated in degrees Celsius for a doubling of CO2. And we see here different model exercises, so coupled model intercomparison project 5 and 6. The 6 was 2019, but also the IPCC 2013. They all had a very wide range from, something like 1.5 to up to, in the last CMIP project, up to 5.5 degrees of warming for a doubling of the CO2 concentration. Now, the newest data you can see here, actually, it's from this year. And they are now constrained a little bit better. And they say that we on average have something like 3.2. All the models on average show that we should have something like 3.2 degrees of warming by a doubling of the CO2. However, the same paper also tells us that it cannot be ruled out that we have even more than 5 degrees of warming for a doubling of the CO2. So that we are up here, it cannot be ruled out. It just can be ruled out that we have a lower warming than 2 degrees by a doubling of the CO2. So a very significant warming can occur. And the reason why this is so unclear, right? I mean, in a way, this is because we are having a lot of different, measures behind this type of doubling. And it's not just a physical thing that we have. We have ecosystems that respond to the CO2 that is brought into the atmosphere, and so on and so on. And that take up more or less carbon, and that also goes into this type of carbon sensitivity measures. Now, why do I tell you that? Because this is important to understand if you look into warming projections. Now, if you take like a climate sensitivity of 3.2 degrees, And those authors have put it into a model and look into this type of baseline, they call it baseline projections. And baseline here means baseline fast. The red line means a relatively aggressive 80% reduction in the energy intensity of our economy. Then by 2050, we would have a warming of around 2.2 degrees. If we have baseline default, which means we have just a little bit of reductions, but not too much, we almost have the same type of warming. So that's the first message here. So until 2050, not much is actually happening. Only if you go to 2100, to 2100, then you do see that there is a difference in the warming. So in the short term, what we do will not have so strong effects than in the long term. But what I also wanted to show you here, this is a probability density. So it's not that we can say, well, if we do this and that, we'll get a specific warming after a while, but it's a very wide density function. And we can get for this type of scenario, everything between 1.5 degree of warming, but also 4 degrees of warming, which is an enormous spectrum of the warming that is possible in the future. And I just want to show that to you because it's so important that we understand, all of us understand, that if we say we can reduce the risk of getting over 1.5 degrees or 2 degrees of warming in the future, it's just that we can reduce the risk. But we cannot really target it specifically because our models are not precise enough and we cannot predict the future precise enough to actually show it. Now, these authors have actually also tested like scenarios where they introduce being carbon neutral quite in 2050 and also removing CO2 from the atmosphere and many other things leading to this green function, right? And what I want to show you here is really the so-called Fattail risk, because what you do see is this probability function, that would reduce the, on average, it would reduce the risk to get over 1.5 degrees of warming, but it has a fat tail. And this fat tail means that with a low probability, but with a very high impact, we can get over 2 degrees or even over 3 degrees. And there is still the risk that we get there, and we have to overthink about it, even if we try to have a scenario that limits the warming below 2 degrees. It doesn't necessarily mean that we will succeed. And we always have to keep in mind that there is a risk, that we are getting well above 2 degrees, even if we try to be below it. And that's important, I guess, for our discussion later on. By the way, if we get over 2 or 3 degrees, this will have rather catastrophic type of consequences. And if you really get to something like 5 degrees of warming, that could well be in this century, then we really get in a completely new state of the climate with rather unknown type of consequences for humanity. So keep the fat tail risk a little bit or keep it in your mind, because that always is just that we are talking about probabilities, not that we are talking about what will really happen. Now, why are the projections that we have are really so uncertain? I mean, certainly because the climate system is really highly complex. It's nothing that you can be easily modeled. It's highly complex and it's non-linear, right? And this is seen here a little bit. So if you just see the temperature records here up to, the early 2000s, you do see that there are different trends that you have. You can have the red line, which is type of a non-linear function that is over it. You can have a decadal D-trend of this function, or you can just have linear functions that are green lines that are very different or very sensitive to the starting point of when you do these linear relationships. So what I just want to say here, it's really non-linear, and we cannot simply project with a linear function in the future. Now, there is also something else, that the climate sensitivity that we are measuring is not just the CO2 alone, but it's also the feedbacks that arise from the warming itself. And feedbacks or climate feedbacks are any type of processes that either amplify or diminish the effects of the climate forcing, which would be, for example, the CO2 or the warming. So that means amplifying is a positive feedback because it positively affects the process behind, or diminishing is a negative feedback. So feedbacks are really important, and we'll talk a little bit about feedbacks in this talk. Now, what type of feedbacks are there? There are purely physical feedbacks, for example, and I will just give you 2 examples in a minute. The summer sea ice albedo feedback, but there are also biological feedbacks, like what happens when permafrost thaws. Now, you think that thawing of permafrost is a physical process rather than a biological, and it is, but the release of CO2 or methane from this thawed permafrost is definitely a biological process, because there are microbes behind that have to decompose this organic material that is being thawed. So we have here, for example, things like that, or we have reductions in land and ocean carbon uptake. For example, also we have the Amazon dieback, right? That could be a biological feedback. I'm not going into all those feedbacks because that takes much too long. However, I will give you some examples so that you can have a better look. Just one thing that I want to mention, many of the physical feedbacks are already at least partly included into Earth system models that do the projections, but rarely are biological feedbacks implemented properly. Yeah? And this is one of the things that I will just show you today, that there are many things that we do not yet have implemented and that are not part of our predictions in the immediate future. Now let's start with simple feedback, the sea ice albedo feedback. So you know that sunlight, when it enters the atmosphere, part of it is reflected back from the clouds to space. Part is absorbed in the atmosphere itself. And then the rest is going onto the Earth. And then it depends where it comes to the surface. If it comes to snow or ice that is white, a large part is actually reflected, and this is called the albedo. And the lower part is absorbed, meaning that we are radiating back energy that is not taken up by the ecosystems, right, by the snow or by the ice. However, if it actually comes onto open water, for example, we will absorb most of the energy, more than, in this case, more than 90%, and only a small part is reflected back to space. And that's the simple thing about the albedo. So when the sea ice is shrinking, then less or the more energy is actually taken up and less is reflected back, and the albedo is getting lower. And that's behind this feedback. Now, the Arctic sea ice extent is shrinking. You all know that. You have heard it many times, I guess. And this is just one of the figures that you can find. Showing this, we have a constant from here, the 1970s to the 1990s, a constant decrease in the winter and the summer sea ice extent. But specifically in the summer, the sea ice extends. Yeah, so the area of the ocean with less than 15% sea ice is strongly decreasing, right? Now, that means that we have much more open water that can absorb more energy, obviously. But that's not the only thing that we have, because in addition to this, we also see that the ice is becoming younger. So this is like from 1985. That's a picture. Here you see like the Canadian and the US coast, Greenland, and the Siberian Arctic. And you do see here, this was then, in this case in March 1985, was still covered by ice. And most of this was red, and red means more than 4-year-old ice. Right, there is a little bit of some younger ice that was just between 1 and 2 years old. And then you see all these other blue areas are just new ice that vanishes every year. But if you look now into the same March 12th in this year, right, what you do see, and I think this is quite significant, is a strong reduction in the age of the ice. So we do not have this perennial ice that stays for more than a year. And large areas that have been old ice before are now completely only new ice that have been frozen once. And that means that this is also open during the summer. And you also see it here with the years, yeah, from 1985 to 2020, we see a strong decrease in this red area, which is the old ice, and a strong increase in the young area. So it's not only that we have less area, the area that is still having ice is much younger and much thinner ice. That is also more prone to being thawed than in the next season. And what does that mean? So I just found this paper. It's a little bit an older paper, but I think in principle it's relatively the same. So they compared the sea ice in September 79 to September 2012. And they calculated the change in the albedo. And when they looked at it, then they said the radiative heating due to the sea ice retreat was for this period of time 6.4 watts per square meter. And this is, well, just a number, but if you think about it, it's equivalent of approximately 25% of the radiative forcing of the CO2 for the same period of time. So that's very significant. And we have a strong warming. Yeah, fortunately, most of this heat was taken up by the ocean, but it's not vanished. Yeah, it's not heating the atmosphere directly. It's also heating the ocean. But that's a very significant amount of energy that has been additionally taken up by these systems. Now, there are projections when the sea ice will, in summer, will disappear completely. And in the earlier model comparisons that we had, 2007 or 2013, this was like, relatively late. So it was in the 2060 or so. And here we had a large spread, but still most of that was around, these are the blue dots, by the way, around between 2020, some models said, but up to 2080. But if you look now into the newest model comparisons, we do see that they are all much lower. And this type of 2 points here that I'm showing you, especially this one here, star, is from a model that was specifically calibrated for, the last ice age that we had. And when you calibrate those models to a last ice age, where we really had a similar situation, where we had warming at an extent to what we had today, then you can calculate that it may already vanish by the mid of the 2030s. And that's also other modeling exercises have shown that it may be quite soon that we are losing the summer sea ice completely. Right? So we can definitely say this could be something like a tipping point. That, by the way, is the climate sensitivity in degrees, or in this case in Kelvin, right? And you do see that if that is true, would be similar to like a climate sensitivity of 5 degrees, which is much higher than we have found with other methods. Okay, that was just a little bit about the sea ice albedo feedback. So it's a feedback that is purely physical in this case, but a very strong feedback. Now that brings me to the point of, is there a threshold in which the sea ice vanishes completely, or what is a threshold? Now, let's think about what a threshold is. If we have a system state and a forcing, then we can imagine that we have type here of a basin of attraction, somewhere where we have like this type of ball, which would be our system. And when we try to remove, we go to the forcing, which could be warming, for example, we remove this here with the warming up here, then there is a strong negative feedback that keeps the ball in this basin of attraction, right? And that means that we have a strong negative feedback keeping the system stable. So what we basically have here is a stable equilibrium. However, if we can get, by just increasing the forcing, the warming, for example, this ball up here, then we have an unstable equilibrium, because it could either go this way back, that would be a negative feedback, or the other way, which would be a positive feedback. And obviously this makes a huge difference, because with this positive feedback, we get a very fast change to another system state that is far away from the stable equilibrium that we had before. Now, this threshold can be defined. I mean, it's just one possibility of definition of a threshold as a point at which the system changes from a negative feedback that stabilizes the situation as we have it to a positive that leads to a completely different system, and this very quickly. Now, what defines such a threshold? What components are there? I think there are two, basically, that you can identify. One is an abrupt change. So a climate response, when a climate response is faster than the forcing, yeah? So if it goes very fast away from here, right? If the forcing is only little, but you have a very strong change, then that is an abrupt change. And the other feature that we would have here for a threshold is a hysteresis. And that means that the system does not return to the original state. So you can, if it's down here, you cannot bring it back. It does not return to the original state after the forcing is removed. So if you are down here and you remove the forcing, you have to wait until it gets back, and I will just show that to you. So a threshold that you have occurs if either you have an abrupt change and or a hysteresis response starts. So something that you cannot reverse anymore. Now, if you have a tipping point, it's in principle nothing very different to a threshold. It's just that the tipping point is defined as a critical threshold. So that's from the glossary of the IPCC report on global warming of 1.5 degrees. And it says a tipping point is a critical threshold when global or regional climate changes from one stable state to another stable state. Okay, so that's the definition of tipping point. Now, that could be like that, and I've just drawn this, sorry for my handwriting. So you would have a system response here, right? And you have a control parameter here. Let's say that's elevated CO2 or the warming or whatever you have. So if you increase the warming, yeah, or the CO2 concentration very long, you don't have any change in the system, right? So the system stays stable because I told you that there is a force that goes against, getting the system out of this system. Then you have a point where you have a very fast change, right, of the system response at a very low type of change in the control parameter. And that's the typical characteristic of such a tipping point, okay? And then you have another system response that is not changing much when you change again the control parameter. Now that would be like a tipping point, and this is a simple tipping point of a highly non-linear system, obviously, because it's not a linear response, but a monostable system. We only have one stable type of equilibrium here, and it's reversible, because if you go back from warm to cold, then you will have exactly the same thing happening, right? So at some time point, you will quickly change back to the original state. And that's the feature of such a system. That's not our main concern, these type of systems. The main concern are the systems that are looking like this. They are called bifurcation tipping point. Should say tipping point here. So what we have here is like the same situation like before. We have not much change in the system response when we change the parameters like the warming until you come to a specific point. And then if you have a small change in warming, for example, you get a very strong change as before. Here we have a stable situation, here we have an unstable situation, and here down here we have a stable situation again. So that means that we have a stable situation for the same temperature. If we would have a temperature here, we would have the stable situation, an equilibrium here and another one here. So we have a bistable system. It's also highly nonlinear, but now it's becoming irreversible. And I just showed it to you because we have this type of equilibria, the stable systems. And in this part here, we have two bistability, two stable situations. Now, that may be theoretical and not so clear for you, but I am trying to show you that in an example. But before I just tell you, bistabilities are quite common. For example, if you're kayaking, right? Then you can have either this type of stable system, but if you lean over too much, then it gets into another stable situation that's turned up. To bring this boat upright again needs energy, and the same is here, right? So there is a negative feedback first until it's taking over, and then there is a negative feedback again that you have to bring it in the other situation. But now let's see how such a tipping point in reality looks like. Now, this is for the Greenland ice sheet. And here is Greenland in 3 different equilibrium states, and we're just looking into E1 and E3. So that's the state that we have today. So a system where Greenland is fully glaciated with a strong ice sheet. And the change E3 would be mostly a deglaciated system, right? There are some glaciers left, but in principle, that's what it is. Now, let's look into this stability analysis. Now, we have here the volume of ice, that would be our system parameters before, and the temperature anomaly. Yeah? Now, what happens is, for a very long time, if you go along this temperature anomaly, if you're warming, right, not much is actually happening until you come to a point, which here would be in this analysis around 1.7 degrees temperature anomaly, where you have a very quick change in your, or just a few tenths of a degrees would change the system state completely to a more or less ice-free state. Now, if I say fast, that doesn't mean that it is fast in time, because it takes hundreds of years until you lose the ice completely, but fast in the sense that it can, when it reaches this state, it cannot be reversed anymore. Because if you go from the other side, from this ice-free state and want to get back to the glaciated state, you have to go much more back in the temperature, down to 0.3 degrees temperature anomaly, until you can regain the ice. And the reason in this case is easy to understand, that why I'm bringing this example, because this is an elevation ice feedback. If you look here, most of the ice is very high. It's up 3 kilometers or 2.5 kilometers on average, right? So in this elevation, it's pretty cold. But once the ice is thawed away, you are on sea level, or even below sea level if the ice is removed. So if you are at a very low elevation, you need to get much down in the temperature to actually be deep enough with the temperature to regain the ice. And that's exactly what you have here, this bifurcation type of system. And I think it's a very nice example. There's another stable system in this analysis, but I'm not going to explain this. So tipping points can be quite complicated, but in principle, they're always type of the same thing that we are looking at. And I will just give you some other examples in a minute. Now, what tipping elements or tipping points do we have? There are quite some tipping points, and there are just a few here that I would like to mention. So we definitely have this type of sea ice that we already were speaking of. We had the type of a Greenland ice sheet. There is the boreal forest, and that is changing on the southern fringe. It's drying, right, and dying. On the northern edge, it's actually going into the tundra already. We have the thawing permafrost. I'm just going to talk about this in a minute. The Amazon dieback, right? We have here the Western Arctic and the Eastern Arctic ice sheets. So I will come back to some of them, but not too many. Basically, those two we have already looked at a little bit. And now I'm going to the permafrost, which is my specialty, if you want so. So the permafrost thawing. Now, the permafrost climate feedback, it's a very prominent feedback with a lot of potential to be devastating. And this is a very nice landscape from the Canadian Arctic, I guess. And below this landscape is permafrost. So what is permafrost? It's permanently frozen type of ground. And I'm just showing you, before I go into this permafrost, a few examples of what's happening. This is like a movie now, and you see the 1990s. That's a temperature movie. We have dark blue is cold, warmer temperatures, anomalies up to 3 degrees is here. We have 1950, it's getting more yellow, 60s, 70s, 80s, the 1990s, that's now the 2000s and the 2010s. And what you do see is that we are getting an increasing temperature increase, but that's not the point here. What I want to show here is that this increase is much stronger in the Northern Hemisphere and specifically much stronger in the Arctic region, so above 65 degrees north. So the Arctic is warming, and it's warming really faster than the global average, 2 to 3 times. We have already more than 2 degrees of warming in most of the Arctic. And we speak about polar amplification, but I'm not going to discuss this at the moment, but it's really hotter there. And the other thing is, and I just want to show that to you, that we have much more heat waves in the Arctic than elsewhere. And this is just from July 2019, so the last 2 years, these huge heat waves that we had, that's now the September, October, the November, so that was cool enough, but then comes the December, it comes the February, 15 degrees above, the average. Again, the same in April and in May. So you do see we have very strong warming in parts of the Arctic, that's the central and western Siberia. So in parts where we have a lot of carbon into the soil. And this enormous warming could also lead, especially if it's in the warmer time, not only in the winter, leads to a starting of, like this permafrost thawing. Now, permafrost, as I said, is a large area worldwide or circumpolar, and permafrost is defined as any type of ground that is below 0 degrees for more than 2 years. And it covers at the moment 22.8 billion square kilometers, approximately 16% of the global land. Now, large areas in Russia, in the Russian Far East and Siberia, but also in Canada and the US, and certainly also in Greenland, is a permafrost area. Now, permafrost area is so important because we have a lot of carbon stored there. And this is like the carbon in the permafrost itself is around 822 gigatons in some of the analysis. And the total northern permafrost region contains something like 1,300 gigatons of carbon. And just to set this in the perspective, that's the gigatons of carbon that are in the atmosphere. So currently we have 880 gigatons in the atmosphere. We have about the same in the permafrost itself and clearly more in the permafrost region. The vegetation globally, for example, is only 500 gigatons. So there's a huge amount of carbon stored in this type of soils. Now, permafrost soils have an active layer, so that's the part that is seasonally melting and thawing. And then there is like a part that is the real permafrost that is usually having a lot of ice wedges and ground ice and contains on average something like 33% of the total carbon of the permafrost region, while in the active layer we have something like 37% of carbon. And that's how it looks like. That's a permafrost soil, not very spectacular. In this case, this was maybe like 60 centimeters deep. Here is the permafrost table. You can't see it, but it's hard. And you see that there are a lot of different horizons. I'm not going into any details here, just to show you that this is a very dynamic system where you have a turnover of material from the above goes into the system down here and so on. So that's unspectacular in a way, but it holds a lot of carbon and this carbon is potentially vulnerable. There is another part of carbon that is sometimes below this type of active layer, and that's the so-called Jedoma. Jedoma is like a type of sediment. And you see that here, that's a crazy Russian that you will see in a minute in another experiment. Sergei Simov, and this was in Eastern Siberia where we were standing in like this part of soil profile where you can see huge ice lands, yeah, and this type of Jedoma soils here. Now, what is Jedoma? If you look closely, you see type of sedimentation, which you normally don't see in the soil. And that is because that is a sediment and the sediment ice complex. So we have sediments here and we have ice. And the sediment is actually Aeolian sediment because this region was not glaciated during the last ice ages. And there was simply not enough water to make big ice sheets there. And because this was not glaciated, wind was blowing soil to it and sedimenting it at a rate of up to 1 millimeters per year. And even now we have very often 25-meter deep Jedoma sediments, sometimes even to 60-meter deep sediments. And this covers something like 1.5 million square kilometers still. And one of the features that is interesting is that these sediments contain a very high proportion of organic carbon. That's the same proportion of organic carbon than a normal soil has, even more than any type of agricultural soil would normally have. And the roots that you see here, they are not coming from up there and penetrating down to here. These are roots that are leftovers from the last glaciation. And once we took one of those roots and dated it, and it has been 27,000 years old. So they are looking like they have been frozen yesterday when they are just thawing, and they're really old material there that can easily be decomposed. And just to give you an idea on how big those Jedoma deposits are, here are two persons. That's from a paper from a colleague. There are two persons standing here, and you see these large Jedoma deposits, and you also see these enormous ice wedges in between. This is just frozen water. This will be becoming important a little bit later on. Now, I know this is just a table and not very interesting for you, but if you just get best estimates for this, we see that we have in soil something like 1,000 gigatons of carbon in Jedoma, another 200 to 400 in deltaic sediments, another 100 to 250. So in total, we get something like 1,300 to 1,600 gigatons of carbon. Gigatons in petagrams, 10 to the 15th gram. There's also subsea permafrost. I'm not going into any detail here, but there is also carbon stored subsea permafrost. But that's all type of the permafrost region that we have. Now, what happens to the carbon if it thaws? The feedback loop is the following. We get elevated temperatures, as we do in the moment. This leads to a thawing of the permafrost. This means that organic material that was previously frozen and could not be decomposed, because in a deep freezer you cannot you put your food in a deep freezer so it's not decomposed, but here it's the same. So if it's frozen, microbes that are in that soil, frozen too, cannot decompose the organic material and make it to CO2, but once it's unfrozen they can. And this warming accelerates not only the microbial decomposition, it makes also the carbon available for decomposition, and that means that they will decompose it and release CO2 and methane. That is depending on whether they have oxygen available or not. And this is then going into the atmosphere again, further leading to, further warming, and this warming then further goes into this type of cycle. And that's called a positive feedback loop. That's easy to understand. Certainly, in reality, it's not that easy. First, what needed to be done is to show that the microbes that are there, if they thaw, can really decompose the material that is there. That has been shown in the meantime quite often. For example, that's a study that one of my postdocs did a couple of years ago, where we could really show that irrespective of the organic material in the soils, it can be decomposed if it's, let's say, brought to 10 degrees instead of freezing temperatures. And after 25 weeks, we had several percent of carbon lost. And the interesting thing is here that the permafrost carbon was actually decomposing as well as the topsoil carbon, and much better than what is in the active layer. So there is so much of carbon there that can be in principle decomposed that yes, thawing this material can be pretty dangerous. But then you also have plants, and plants take up CO2, and we know that the Arctic is greening, right? At least you may have heard of it. So because it's getting warmer, plants grow better, and they grow, in different patches, they grow better in their size, they get bigger, and they also go northwards, right? So shrubs and also trees expand towards the north. So yes, the plants grow better, and you can also see that in such analysis where you do see and so-called Arctic greening. So each of the pixels here has a color, and if it's green, then it was increasing, the plant production compared to previous states. And you do see that wide areas of the Eurasian Arctic, but also of the North American Arctic, is actually greening, so plants grow better, while other parts here are browning. This is especially where it's getting drier, and then plants cannot grow that well. But overall, we have an Arctic greening. So plants grow better, and we could say, well, maybe microbes respire more CO2 to the atmosphere, but at the same time, plants take up more CO2. So that could be, in this case, a negative feedback leading to a reduction of the CO2 concentration in the atmosphere. Well, that's okay, but in principle, it's not very likely. So if you make a very simple calculation, at the moment we have about, in the boreal permafrost area, you have about 60 gigatons of carbon in plants, and in the tundra about 3 gigatons of carbon in plants. Now, if you look into the concentrations and you make a simple back of the envelope calculation, and you say, well, if all the tundra will get boreal forest, which it will not, at least not in the near future, then how much carbon can be additionally stored? And what you do see is that the maximum increase that you could have in plant biomass is something like 25 gigatons of carbon. Well, that's okay, but it's not a lot compared to what can be released from the soils, obviously, right? So there is not likely that we have a strong negative feedback by plant carbon fixation. In fact, it's rather unlikely. And if you look into the carbon balance of the Arctic, that has been historically always like a sink of carbon, so taking carbon up, yeah, so that's why we have so much carbon in the soils. It has already changed to being sources of carbon to the atmosphere. And this is like an older paper, but there is also now newer papers that clearly show that almost all Arctic systems that have been looked at more closely show that we do have Arctic systems, or the Arctic systems have already become CO2 sources. So this is like the net CO2 release. Yeah? So if it's above zero, it means a release of CO2 to the atmosphere. And if it's below, it's an uptake of CO2 from the atmosphere. And you do see that during the growing seasons, almost all of these systems along the mean annual temperature gradient are taking up CO2, they should. But in winter, they are strong emitters of CO2. And because we have seen before that we have quite warm temperatures in the winter very often, this leads to an annual loss of carbon across the whole gradient of different temperatures. And that is quite significant. So in this study, it was around 50 grams of carbon per square meter a year, what is lost. And that would mean about 1 gigatons of carbon for the whole Arctic per year. That's quite a bit. So that would be 100 gigatons in 100 years, right? Just that you get a dimension. Now, the IPCC has also reviewed those things. So there was this special report on the oceans and the cryosphere in 2019, and they also speak about 37 to 174 petagrams, which is the same like gigatons of carbon by 2100. So that's in the same range that the other studies actually show. Okay, so there was another complexity, and I just want to bring that as the last point, because I just want you to understand that these things are not so easy to and not so linear. Because what we also have is that the plants that grow better, and we just spoke about it, also affect the microbes in the soil. So when plants grow, they exude in their roots or in the vicinity of their roots, they exude carbon, and this carbon helps the microbes that live there, right, to decompose the material, the organic matter that is already in the soil and is thawed. Now, this is called priming. So priming is plants put in a little bit carbon, but much more from the available carbon here is then decomposed and getting into the atmosphere. Now, what we did in a study a couple of years ago with a lot of colleagues all over Europe is to look into what happens if the soils are now thawing and getting deeper, because then the plants grow better, obviously, but also the roots penetrate deeper and bring carbon into deeper soil layers. And we looked into, does this have an effect on the carbon balance of those systems? And in this modeling study, what we could say is that, and this is just like a map showing how and where carbon is specifically released. We could show that 40 gigatons of carbon could be additionally released by this priming effect until 2100. So that's a lot. And this is carbon that is not yet accounted in any model. Yeah, also not accounted in any IPCC report. So things are getting quite complicated. But let me say the last point here in the permafrost, and that is abrupt thaw. So if we look into the permafrost landscape, then we see that in the soil very often we do have ice wedges, yeah? Not always as big as the ones that we have just shown in the yellow map, but also quite significant ground ice. So that's ice that is finely distributed, or ice wedges. In these lowland areas, for example, here in these high center polygons or low center polygons, which is a degradation, you see a lot of ice that is degraded over time and then leads to the water that is standing in this type of polygons. Now, why are we interested in this? Because this abrupt change is very different from the gradual change of temperature that we were just speaking about. Change in temperature and precipitation is usually a slow change that is more a press, yeah? A continuous type of disturbance for a system, which has much less impact than if you have a physical disturbance that is abrupt. Very often fires can lead to an abrupt change in, this type of frozen state. And this is then called a pulse, a discrete disturbance. Now, in these ice-rich permafrost areas, in these thermokarst systems, this very often also leads to the collapse of systems. And newer results show that up to 4 million square kilometers in the permafrost region is actually prone to abrupt thaw processes. And that's how that could look like, right? So you have a landscape, and then suddenly in the landscape, you have complete collapse. And that was because ice in here, right, was starting to thaw, maybe because the isolation of the vegetation was, by whatever reason, removed. And then you have an overturning of the whole system very quickly and in large areas. And that certainly makes a big difference. So in a study that was last year published in Nature Communications, the authors analyzed Holocene deposits with ice wedges, drained lake basins, Jedoma with large ice lakes and so on, and looked into what happens there. Now, just to give you some ideas how that looks like, active layer, right? Ice wedges, normal permafrost below the active layer that is usually not having a lot of ice, but then getting to this ground ice where you have lower permafrost, where you have a lot of ice, that if it's getting type of thaws, you have a lot of mud that is just flowing around basically. And there's again this Sergei that I told you before, this crazy Russian scientist who is living in Eastern Siberia, and he had this idea to show what happens when you remove in a large scale the isolating part of such a system. And what he did is he took type of I don't know how this is called, excavator, I think it's called in English, this type of machines where you can remove in a large area, remove soil. And what he did is just taking away the isolating top centimeters of that soil that contains the mosses and the lichens that isolate the soil against the atmosphere, no? So that the atmosphere is not directly warming the soil. And he did this for a large area, several 100 square meters. And what then happened is the following. In 4 years that followed this type of removal, you see really where the ice was and how the system was degrading completely. So that's 2 to 3 meters deep. Unfortunately, I don't have a sign here how deep it is, but that's more than the height of a person, right? So it's really deeply thawed in here, and a totally collapsed system where a lot of CO2 and methane was actually getting out. So yes, abrupt change is easily possible, and it happens on large scale. And a landscape can look like this at the end, right? So that's another Siberian landscape where this has happened before, and that's what then the leftover is. You can easily imagine how much carbon also was lost here. Now, one of the main reasons why this type of abrupt changes occur are wildfires. And we have heard that wildfires, specifically also in the tundra fires, but also northern boreal forest fires, were actually in large parts of the Arctic prevailing in the last years. And what happens then is that you have a much deeper thawing of this type of active layer. You have type of rapidly thawing permafrost. And what is also happening is talik formation. What is a talik? A talik is a large lens or area where when it's once unfrozen by a forest fire or similar, it does not freeze again, also not in winter, in the next winter. And the reason for it is because it gets once warm enough that the microbes start decomposing. And if microbes, like any other organisms, work, they also emit energy, right? They are getting warm. And this warm, this heat that is actually released, keeps the talik unfrozen. So that's a self-sustaining system. And this can be unfrozen for many, many years. We know that there are taliks for more than 30 years in place. And if that is unfrozen also during the winter, they can 365 days a year can decompose organic material. And this organic material is then coming as CO2 and methane, again, mostly methane also in the atmosphere. So this talik formation is quite significant. So gradual thaw, as we had before, versus abrupt thaw. So if there is a lot of ground ice lost quickly, then you have the development of lakes and the development of taliks. And my last slide that shows you that is here, like these thermocast systems. And here we have 1949 aerial photographs to 2010. And you see the expansion of some of the bigger lakes, but also the new lakes like this one here, is just developing over the time. Yeah? So it has really developed from not there to fully there. And when you then look into the current situation, then you see that there are 20 meters or even more of the permafrost completely lost. This is a talik below or completely degraded. And that's huge. There is a huge area below this type of lakes that are producing methane. And that's just showing it. So here you have the gradual thaw. And here you have, this is not much of an exchange of CO2, for example. And here you see how much methane or CO2 is exchanged when you're below these lakes or in the vicinity of these lakes. Enormous amounts that are very, very relevant for the future. So permafrost thaw is a tipping point, definitely. We have about 100 gigatons by gradual thaw, we know that. It's really unclear what proportion of this 100 gigatons is already accounted for in models. That's not so easy. Yeah? Then we have the priming additional 40 gigatons of carbon not accounted for. Abrupt thaw, we just know that it's 3 to 12 times more carbon will thaw when this happens, but not how much CO2 actually comes in the atmosphere, but it's a lot, most likely not accounted for. And if you keep that in, or set that in relation to the carbon emission budget that we still have to get a 50% chance to stay within 1.5 degrees, it is 120 gigatons of carbon. If you just sum that up, it's already clearly more. So this carbon could bring the climate to a tipping point, definitely. Now, I'm not going into detail here, just to show you there are a lot of different tipping points. And the idea is now that there could be cascades of tipping points. So not just one, but one is leading to the next and to the others. So I'm just have mentioned a few here, and I'm not going into details, but just showing you summer sea ice loss, permafrost thaw, and also rainforest dieback all amplify warming. So they are really leading to further warming, right? The boreal forests shift, West African monsoon shift, Indian monsoon shift lead to strong ecosystem changes and maybe some additional carbon. And also these ice sheet disintegrations that we have in Greenland, West Antarctic, East Antarctic lead to various levels of sea level rises. By the way, this is not true. This is 30 centimeters. There are newer, this is an old slide, sorry. And there are newer analysis now that it's maybe not 1 meter, but even 30 centimeters is a lot. Okay, so cascades that could eventually lead to dramatic situations. Now, early warning signs, can we detect this type of point when a system changes strongly? Well, we could. There is, at the end here, there's something which is called critically slowing down, which means that if you have further perturbation here, right, you have slow recoveries from the perturbation near the tipping point. However, to detect this properly, you need high frequency long-term time series. And these are very often not available. Now, think about the permafrost. Nobody has long-term high frequency data on permafrost development, obviously, right? Now, it could be, however, that if we have that, we can see that there is an increased variance in the data and also that there is an increased autocorrelation. And if we see there is a point coming here, then we could say, well, now we are near to this tipping point. But does it help us? No, it doesn't. Because once we are there, it's most likely already too late to stop it. So the point is that we have to type of minimize the risk, and that is just stay long on this side. And the only way to do that, if we cannot say exactly when this tipping point is coming, is to emit as little as possible. What can be done? Well, what I'm hoping that can be done is that we are going into a decarbonized state of the Earth. And there we need to have something like social tipping interventions or social tipping points. Obviously, what we need is we also need to get over this type of point where we get into the decarbonized state. And we can do that in a non-physical system like the social ones by reducing this type of resistance against getting in a new state. But we need to bring our business as usual state into a decarbonized state, obviously. Quite nice paper that we have here from Ilona Otto in PNAS from last year. Now, the reason why we have to do is to get in a trajectory that actually leads us from the Holocene, which we are not anymore, we are in the Anthropocene, leads us to a future that is safe and just. Safe in the sense that we are staying below a certain warming so that many of these tipping points will not be reached. If we do not go there, we will get into a very unsafe future where we have maybe 4 to 5 degrees of warming with completely unclear, but most likely catastrophic type of futures. So this is the end of my talk. Now you know why I maybe choose that. That's the times they are changing, 1964, Bob Dylan. And it says, then you better start swimming or you'll sink like a stone, for the times they are changing. So let's hope that we are not going to sink like a stone and that we start swimming soon. And with that, thank you very much for your attention.